Hey guys, it's Mark here. I'm just going to run through how to do planar truss analysis using the method of joints. Before we do that though, I'm just going to remind you of the conventions that we use with axial forces. So forces acting away from the center are called tensile forces, and they're denoted as positive. Forces acting towards the center are compressive forces, and they're denoted as negative. The other thing I'll remind you of is how we split a force that acts at an angle into its components. So F here is acting at an angle theta to the x-axis. So the horizontal component, called Fx, is simply F times cos of theta. And the vertical component of F is Fy, and is simply F times the sine of theta. So with that out of the way, let's get into it. Here we have a truss with two external forces, one acting vertically down at B, and one to the right at D. This truss is supported by a pin joint at C and a roll support at A. So let's go ahead and replace those supports with their respective reaction forces. So the pin has been replaced with Cy and Cx, and the roller support has been replaced with Ay. We can calculate theta fairly easily, as it's simply the inverse tan of 4/3, which is the height of the truss divided by half the width of the truss, which gives us 53.13 degrees. Now, before we can find any of the internal forces of the truss, first we have to find the external forces. We'll start with the horizontal forces. We can use our equations of equilibrium using the convention that right is positive. So we have 600 minus Cx is equal to 0, so we get Cx is equal to 600 newtons. Next we'll take the moment about C, because this gets rid of the unknown Cy and allows us to find Ay. We use the convention that counterclockwise is positive. So we have 400 newtons acting 3 meters away from C in a counterclockwise direction, plus 600 newtons acting 4 meters away from C, also in a counterclockwise direction, and then Ay is acting in a clockwise direction, 6 meters away from point C. Rearranging, we find that Ay is equal to 600 newtons. Finally, we take the sum of forces in the vertical direction, taking upwards as positive, and here we get Ay minus Cy minus 400 is equal to 0, and find that Cy is equal to 200 newtons. So that's all fairly simple stuff. So the method of joints works by taking a joint that has at least one known force and no more than two unknowns. Now, given that the joint is in equilibrium and is a static object, we can take the sum of forces acting on it to find the internal forces of the members of the truss. So here we'll start with joint A, just because it's the simplest, where we have two unknown forces acting through members AB and AD. Using our equations of equilibrium, we can show that in the vertical direction, Ay plus AB times sine of theta is equal to 0. Now, by drawing all the internal forces as tensile, the sign of your answer will dictate whether the force is compressive or tensile. Since the sign for the force in AB is negative, we can conclude that it is actually a compressive force. Remember, this only works if you initially assume that all your internal forces are tensile. We'll do the same thing in the horizontal direction. AD plus AB times the cosine of theta is equal to 0, and this gives us that AD is equal to 450 newtons. Since this is positive, then it's a tensile force. Now we'll move on to joint C. This one's fairly straightforward. We first write out the vertical equation of equilibrium, which gives us that negative Cy minus CD is equal to 0. Solving that, we get CD is 200 newtons compressive. Then we do the same for the horizontal direction. So negative Cx minus BC is equal to 0, and find that BC is also compressive with 600 newtons. So now we've solved for all the members except for BD. So we can move to joint D to find that out. We can use either the horizontal or the vertical equations to find BD. We're going to use the vertical one. So CD plus BD times the sine of theta is equal to 0. Again, using the components that we talked about earlier. This gives us that BD is equal to 250 newtons, tensile. And that's really all there is to solving trusses using the method of joints. We have found the internal forces in each of the members, and later on we'll be able to find the stresses that run through each of these.